Now, coming off the last video looking at multiplying matrices, something that multiplying matrices helps us do is talking about finding the inverse of a matrix, right? But to kind of understand, right, what inverses are, you have to go back and think about how were we introduced with inverses, right? The idea of an inverse was that you're able to apply an operation to a value or to an expression, and the operation that you applied left you, and if in the values or the expressions were inverses, if you were left with an identity, right? The first way you were introduced to inverses, which you probably didn't use the word inverses, was when you learned about solving equations. When you were told what you do to one side of the equation, you do it to the other. And what the way you were, maybe the way you remember it taught was, if you see a particular operation, you do the opposite of that, right? If you see a positive 2, you subtract 2. If you see a negative 2, you add 2. If you see, if you look at multiplication, if you have a whole number multiplying by 2, you're going to do the opposite of multiplication, which is division, and you divide by 2. But what you were truly doing was using the inverse of that value within the context of its operation. Now, what does that mean? When I look at, for example, when we added 2 on both sides of the equation, let's say something as simple as this. I'm trying to solve for x. So I subtract 4 to both sides. Now the idea is positive 4, negative 4 were actually inverses of each other. Because when we apply the operation, I'm left with a 0, right? And it didn't matter, right? You could do 4 plus negative 4 give us 0. Or you could do negative 4 plus 4, and that would also give us 0. So it didn't matter the order. Both of those orders gave you 0. Now, they are inverses of each other because the operation in question gave us the identity. Now, in arithmetic, right, in adding and subtracting, 0 was what you'd call the additive identity because of the number that you would apply the operation with, which since it's the additive identity, the operation is adding, it won't change anything. So adding 0 to any number is not going to change that number. Now let's say, for example, x is equal 2x is equal to 4. To simplify this 2, you would divide both sides by 2. But what you're really doing is taking 2 and multiplying it by a half, because 2 and a half are inverses of each other. Because 2 times a half leaves me with 1, which 1 is known as the multiplicative identity. Right? I could do 2 times a half will give me 1, or a half times 2 will give me also 1. So it didn't matter which way you multiply the numbers. As long as these two values are multiplying to each other, you're left with the multiplicative identity. And we followed those same principles even when we got into functions. Because and we've done that in this class, right? When we apply inverses to cosine, sine, we're left with the argument. And the argument, right, we're left with just what was inside. We're just left with the independent variable. That is our identity for our functions, right? And we're going to apply the same concept for matrices. So matrices do have inverses, and they also have an identity, because to have an inverse, for functions we need a one-to-one, but the idea of inverses is that when you applied the inverses to each other, so when you're dealing with functions, the operation in there was composition. For the additive identity, of course, it's addition. Multiplicative identity, it's multiplication. But for the identity of matrices, we use that multiplication that we just did. And the multiplication to have our inverses, or to verify if two matrices are inverses of each other, you have to be able to multiply these inverses, and you're left with the identity matrix. Right? And that's what we have to talk about. What is the identity matrix? How do I know that I have that identity matrix? So the identity matrix is an n by n matrix. So that is telling you what our inverses are going to look like. Is that we're going to be left with an n by n matrix for which the main diagonal entries are 1 and 0 for all other entries. And here's a couple examples of a 2 by 2 identity matrix, a 3 by 3 identity matrix. The main diagonal is 1, all other values are 0. And obviously this will continue to, if it was I sub 4, I sub 5, main diagonal is 1, zeros everywhere else. Now, how do we check? So we're not finding the inverse. How do we check if two matrices are inverses of each other? So you need to multiply in both directions. Now, here's an example of A and B that we did in the previous section, which when we multiplied, we're left, well, these are definitely 2 by 2 matrices. When I multiplied them, I was left with a 2 by 2 identity matrix. So far, it's worked in one direction, but I need to check the other. So I've done A times, I guess we don't know that this is the inverse of A, but if I wrote A inverse, that means we did this part. Now we need to do the commutative, we need to commute them and do this version. Now I did say the commutative property does not exist for matrices, because I can find an example of where this idea, not just for inverses, but just in general, multiplying two matrices where the matrices are commuted, meaning they swapped order, will give you a completely different answer, or will not even be possible at all. So for multiplying matrices, remember that those columns and rows need to be identical. Luckily here they are, right? 2 and 2. But now I'm going to be doing B times A. So this is going to be a little confusing, because writing A times B, I was just looking for the columns in A to be equal to the rows in B. But now that I'm doing B times A, I need to look at the columns of B, which luckily it's 2, and the rows of A, which is also 2. So the column of A inverse is equal to, or B I guess would be better, the column of B, the number of columns in B is equal to the number of rows in A. So that means we will be able to multiply them together. But since I'm multiplying B to A, I need to take the first row of B, rotate it clockwise 90 degrees, and then multiply with the column in A. Now the idea is I want to be left with the identity matrix. I've checked one order, I need to check the second. So that's going to look like this. So if I rewrite this vertically, it's going to be a 3 and then a negative 1. 3 and negative 1, and I'm going to multiply across and add the products together. So that's going to be 3 times 2 plus negative 1 times 5. So first row, first column, right? 3 and negative 1. So 3, 2 is here, negative 1, 5 is here. Now I need to take this first row and multiply the second column. So that's going to be 3 times 1 plus negative 1 times 3. Now I need to take second row, first column. So it's going to be negative 5 times 2 plus 2 times 5. Right, because I'm rotating this 90 degrees to the right. And that would leave me with 5, negative 5, and 2, giving me this particular entry. And now I'm going to do negative 5 times 1 plus 3 times 2, which this very first entry, 3 times 2 is 6, minus 5 gives me 1. Second term, 3 plus negative 3 is 0. Negative 5 times 1 is negative 5. Plus 3 times 2 is 6. That's going to leave us with... Oh, I was doing this one, but I had to do that one. Negative 5 times 2 is negative 10. 2 times 5 is 10. This gives us 0. Here I was saying this is negative 5 plus 6. We're going to be left with a positive 1. Now if you notice, that means I just multiplied A and B in both directions. I did A times B and B times A, and I got the identity matrix in both scenarios. So that tells me A and B are inverses of each other. Now this is going to always help us check 2 by 2, 3 by 3, so on and so forth. But we also have to know how to actually find it. Luckily, there's a nice formula for 2 by 2 matrices. Is all I'm going to go up to is just looking at 2 by 2 matrices. And there is a nice formula that shows us how to calculate the inverse. Now, we can take... So the formula is taking 1 and dividing it by... This is known as the determinant. That's the name for it. You're doing it in a particular pattern. The determinant of A. Or some people might write it as determinant of A is equal to AB minus BC. And then this becomes a scalar that you distribute to each term. But if you notice, it was A, B, C, D. Now it's A and D have swapped. And C and B are in the same place. But now they are negative. So let's see a quick example of this. And the way I always remember it is you multiply A and B, or A and D. So this sort of negative slope, I think, times C and D, which is this positive slope here. So I first want to find my determinant, because that's what I use to make my scalar. So the determinant of A is... it's going to be 1, or the determinant is just multiplying in a diagonal. Putting it over 1 is part of the formula. So the determinant is just 2 times 3 minus 5 times 1, which is going to be equal to oops, made a mistake. So 2 times 3 is 6, minus 5 is equal to 1. So not super exciting, but still A inverse is going to be equal to 1 over essentially the determinant of A, and then that's going to be equal or times changing your diagonal, so that's going to be 3 and 2, and then swapping the signs, so it's going to be negative 5 minus 1. So negative 5 here, and negative 1. So C and B stay in the same place, but A and D do swap between each other. And that's what I got here. Now, I know the determinant because I calculated it. But it's going to be 1 over 1, which is just 1. And then we're left with this. Because distributing that 1 isn't going to simplify this any further. But A inverse is 3, negative 1, negative 5, and 2. Let's do one more example real quick. Like I said, the first thing we want to do is the determinant of A, which is multiply this diagonal. So 4 times negative 1 minus 3 times 2. And that's going to be negative 4 minus 6 is going to give us negative 10. So then all we have to do to find B inverse I have to write the determinant, which is 1 over negative 10. And now we swap the rows. So A becomes D, D becomes A. So it'd be negative 1 and 4. And then you change the sign on that other diagonal. And we have to distribute that negative 10 into this problem. Now that's going to give you 1/10 times negative 1 is going to give you positive 1/10. Negative 2 times negative 10 will simplify to 1/5. 3 times negative 1/10 is going to be positive 3/10. 4 times 1 over negative 10 is going to be it's 4 over negative 10, but you can simplify that as 2 over negative 5. Because 2 goes into 4 2 times, and 2 goes into 10 5 times. And that would be my determinant of a 2 by 2. So hopefully that wasn't too confusing. The idea is you find the determinant, and you do 1 divided by that determinant. You swap the diagonal, and then the second diagonal, you just change the sign. I just want to make this one sweet and short. We're just looking at inverses. And that's all. So I'll stop the video here. So remember, you can't always multiply them in both directions, but if you do, and you're left with the identity matrix in both directions, then those matrices are inverses of each other.